A single rack of artificial intelligence servers can consume up to 100 kilowatts of power, which is nearly 10 times the energy that traditional data centers were designed to handle. We are facing a massive collision between the cutting-edge demands of artificial intelligence and the aging power infrastructure that most companies rely on today. Businesses are rushing to implement generative AI, only to find that the facilities they built in the 1990s and early 2000s are literally buckling under the strain of modern computing. Today, we are exploring how AI is breaking legacy power grids, the intensive cooling necessary to keep these servers from melting down, and the industry shifts happening to fix this, specifically looking at the new partnership between power management giant Eaton and NVIDIA, as well as how organizations like BSD Business Consulting are helping companies deploy these heavy-duty solutions.
The disparity between what we have built and what we need is staggering. When companies constructed their primary data centers in the late 90s or the 2000s, they were building homes for central processing units, or CPUs. Those facilities were designed to host websites, manage corporate email, and run standard database applications. A typical server rack back then, and even up until recently, drew maybe 5 to 10 kilowatts of power. The entire electrical and cooling architecture of these buildings was mapped around that specific threshold.
So if a standard facility is wired for 10 kilowatts per rack, what happens when a company decides they want to train a large language model and brings in a suite of AI-specific servers?
They hit a hard mathematical wall. AI relies on graphics processing units, or GPUs. Chips like the ones NVIDIA produces are incredibly powerful, but they require a massive amount of electricity. An AI server rack easily demands 30 to 100 kilowatts, representing up to 300% increase in power consumption compared to a normal rack. If you put that into a data center built in 2005, the facility's power distribution units simply cannot deliver that much juice to a single location. And even if you could somehow force the electricity through, the heat generated would trip all the thermal alarms and potentially cause hardware failure.
That brings up the cooling aspect, which seems just as critical as the electricity delivery. Traditional data centers use raised floors and massive air conditioning units to blow cold air through the server aisles. I assume that method falls apart when you have racks generating 10 times the normal heat output.
It completely falls apart. Air has a very limited heat absorption capacity. When you are pushing 60 or 80 kilowatts of power through a single rack, blowing cold air at it is like trying to put out a campfire with a desk fan. The server fans have to spin so fast they consume a significant portion of the rack's power themselves, which just adds to the overall energy draw.
It sounds like a destructive feedback loop. You need more power for the compute, which generates more heat, which requires more power to cool, straining an infrastructure that was never designed for this volume in the first place.
That is exactly the problem the industry is trying to solve right now. The infrastructure has to evolve from the grid connection all the way down to the individual chip. We are seeing companies move away from traditional air cooling toward advanced liquid cooling systems, where coolant is pumped directly to the processors. Liquid is much more efficient at capturing and removing heat. But retrofitting a 20-year-old facility to handle liquid cooling and high-density power is a massive engineering challenge.
Which explains why we are seeing heavy industrial partnerships forming to address this bottleneck. Eaton, a major player in electrical power management, recently announced a significant collaboration with NVIDIA. How does an electrical equipment company fit into the deployment of artificial intelligence?
Eaton brings decades of expertise in handling heavy electrical loads. NVIDIA makes the chips, but those chips need a reliable, efficient, and massive power delivery system to function. The core of their recent partnership focuses on transitioning AI data centers to high-voltage direct current, or HVDC, power infrastructure. Specifically, they are collaborating to implement 800-volt HVDC architectures designed for high-density GPU deployments, like NVIDIA's newer rack-scale systems.
Why is the shift to high-voltage direct current so important? Most data centers currently run on alternating current, right?
Most do, yes. Power comes from the grid as alternating current, or AC. In a traditional data center, that AC power goes through an uninterruptible power supply, gets converted to direct current, or DC, for the batteries, gets converted back to AC, and then goes to the server, where the server's power supply converts it back to DC for the motherboard. Every single one of those conversions loses energy as heat. When you are dealing with a few kilowatts, that loss is manageable. When you are dealing with 1 megawatt of power for a row of AI servers, those conversion losses become catastrophic.
So by switching to an 800-volt HVDC system, Eaton and NVIDIA are eliminating those inefficient conversion steps.
Precisely. By distributing high-voltage direct current directly to the racks, they streamline the power path. It reduces energy waste, lowers the heat generated by the power distribution equipment itself, and allows the facility to pack more computing power into a smaller physical footprint. Eaton is integrating their intelligent power distribution, backup solutions, and digital management software directly with NVIDIA's reference designs.
That makes sense on paper, but I imagine the actual execution is complex. A large enterprise or a regional data center provider cannot simply buy an NVIDIA rack, call Eaton, and plug it in. There has to be an intermediary translating these technologies into a functional business environment.
The integration layer is where the real work happens. You have the hardware innovation at the top level, but implementing it requires specialized knowledge of both legacy facilities and modern AI requirements. This is where channel partners and specialized consultants become vital to the ecosystem.
Which is exactly where firms like BSD Business Consulting come into the picture. They operate as an Eaton partner, selling these exact power and cooling solutions to enterprises. If a company realizes their 1990s infrastructure cannot support the AI initiatives their board is demanding, how does a partner like BSD approach that overhaul?
A partner like BSD Business Consulting acts as the bridge between the conceptual technology and the physical reality of a client's data center. They start by auditing the existing power constraints. If a company wants to deploy a cluster of NVIDIA GPUs, BSD assesses the current facility's power capacity, the state of the transformers, the backup generators, and the cooling limitations. Because they sell Eaton solutions, they can map Eaton's high-density power distribution units and advanced cooling containment systems directly to the client's AI roadmap.
So they are not just selling a piece of hardware, they are re-architecting the facility's relationship with electricity to prevent the new AI servers from causing a catastrophic outage.
That is a good way to put it. Deploying AI hardware without upgrading the power infrastructure is like putting a jet engine into a vintage car. The chassis will tear itself apart. BSD Business Consulting helps companies install Eaton's specialized busways, uninterruptible power supplies, and thermal management systems so that the infrastructure can actually support the jet engine. They ensure that the massive power draw is stable and that the cooling is targeted exactly where the heat is generated.
It seems there is a significant financial nuance here. Upgrading power and cooling is not cheap. When companies budget for AI, they often think about the cost of the software, the data scientists, and maybe the GPUs. Do they often underestimate the infrastructure costs?
They almost always underestimate it. The capital expenditure for the physical facility upgrades can sometimes rival the cost of the computing hardware. When an enterprise decides to run their own private AI models for security reasons, they suddenly realize their existing data center floor cannot bear the physical weight of liquid-cooled AI racks, nor can the local utility provide the required megawatts. Partners like BSD Business Consulting have to guide clients through these stark realities, helping them source Eaton equipment that maximizes their available footprint without requiring a completely new building.
That reliance on local utilities brings up another massive tension point. Even if a company buys the best Eaton power management gear through BSD, the local power grid itself has to deliver the electricity. Are we reaching a point where regional power grids simply cannot support the AI boom?
We are already seeing that happen. In places like Northern Virginia or parts of Ireland, the grid operators are pausing new data center connections because there is simply not enough generation capacity. AI data center power consumption is projected to grow substantially over the next few years, potentially taking up a much larger percentage of total national electricity demand. This is why intelligent power management is no longer optional.
So efficiency becomes a matter of survival, not just cost savings. If a grid limits a facility to a strict megawatt cap, any power wasted on inefficient cooling or poor power conversion is power taken away from the actual AI processing.
Exactly. The margin for error is gone. In the early 2000s, data centers routinely over-provisioned power. They would secure twice as much power as they needed just to be safe and run inefficient air cooling because electricity was relatively abundant and cheap. With AI, every single watt is contested. The Eaton solutions that partners like BSD Business Consulting deploy are designed to monitor and route power dynamically, ensuring that the heavy GPU workloads get exactly what they need without tripping breakers or wasting energy on idle systems.
It is fascinating to see how a software revolution like artificial intelligence is forcing a hardware and electrical revolution. We talk so much about algorithms and neural networks, but at the end of the day, those abstract concepts require cold water, thick copper cables, and massive transformers.
The cloud is not ethereal. It is heavily industrialized, and as AI models become more complex, their physical demands will only increase. The partnership between Eaton and NVIDIA is an acknowledgement from the tech industry that silicon advancements cannot outpace electrical realities. The compute power has reached the physical limits of traditional infrastructure.
And the companies that fail to recognize that physical limit will likely find their AI initiatives stalling out before they even begin. If you try to run next-generation intelligence on 1990s electrical logic, the math just will not hold up. That is where the expertise of integrators and consultants, who understand both the compute requirements and the electrical limitations, becomes the defining factor in whether an AI project succeeds or literally burns out.
The modernization of the data center is the quiet, essential foundation of the AI era. It lacks the flashiness of a new chatbot, but without the high-voltage systems and the advanced cooling strategies, none of those applications can exist.
The evolution of computing is forcing an evolution in power, and companies have to address their physical infrastructure if they want to participate in the AI economy. If this breakdown of the hidden systems powering artificial intelligence gave you a new perspective on the industry, send this episode to a colleague who is navigating the complexities of modern data centers.